Hello, I'm Emiliano Dall'Anese from the Department of Electrical, Computer Engineering, and also the Division of System Engineering. So my group is working in the main areas of optimization and control, and the real objective is to uncover new mathematical principles for the design of decision-making architecture for complex engineering system infrastructures. One of the main drivers is to apply these new mathematical models to power systems, all the way down to transmission systems, to the distribution level, with particular focus on distributed energy sources, EV, PV systems, as an example, heat pumps, as my colleague mentioned, all the way down to intelligent buildings and cities. Now, since this is a very diverse audience, let me explain what do I mean by control system. So we have a given system, in this case, a neighborhood or as part of a town with some controllable assets, can be the power of some resources or simply electric vehicles. And what we're going to do is to design an algorithm or a control rule to operate these assets. The way we design this algorithm or rule is based on well-defined objectives and performance objectives, as simple as keeping the light on during a storm, or as noble as addressing CO2 emissions. We also account for operational reliability constraint of the system, or requirement of the system, market structures, and whenever we have the human in the loop, also behavior or responsiveness of the human to pricing or incentives in order to utilize these assets. Now, I can say that overall, what we're going to do is to push forward a new generation of automation and AI for energy systems to solve, again, problems at the transmission level, all the way down to future neighborhoods or smart homes, and with the objective to enable a carbon-free future. Now, why do we need these changes, right? Things work, lights is on, right? Well, if I had to give an example, if I look at the integration of distributed energy sources, the system was not designed to operate with these new resources, electric vehicles, PV systems. Example, if we have overgeneration, we may have overvoltages, thus triggering outages. If all of us have an electric vehicles and we all charge the electric vehicle at the same time, we have overloading, triggering outages. Moreover, now we have a gazillions of new controllable assets that need to be orchestrated in real time in order to enable a reliable system operation. So we're looking at this, how to orchestrate the operation of these new assets, acknowledging objectives, acknowledging new markets, and addressing, again, sustainability and reliability concerns. As an additional example, we are also looking at, with a particular focus on electric vehicles, how to strategically charge electric vehicles during period of the day with high renewable generation. Suppose, for instance, that we have ride-hailing services with a 100% electrified fleet. How do we charge electric vehicles during high solar irradiance or solar generation, but at the same time don't miss too many rides, so that we don't disrupt the quality of service? This is just another example of questions that we're asking. And of course, we can also look at addressing some traffic congestion, for example, in the city of Boston, by intelligently controlling city lights, intersections, and so on and so forth. But the objective is still enabling sustainability. And I will stop here, and I will pass the token to the next colleague.